Hi, as Ben said, my name is Lisa Burris, and one correction is I'm from the Ohio State University, not just Ohio State University. And I was sort of added to this session a little bit later, so it's not going to be as sustainability focused as probably a lot of the other talks are. But I did want to humbly acknowledge a mistake that I've made over the last couple years with respect to sustainability. I think for those of us who've been working in a sustainability-focused research area for a while, we have spent a long time trying to make a case that sustainability is important and that using sustainable materials is important. And we may have done a disservice at this point in a little bit overemphasizing the carbon footprint of concrete and how terrible it is. And so I spent a bunch of time in my classes talking about how we need more sustainable concrete, and there's lots of reasons why and how easy it would be to incorporate more SCMs and other things into the concrete. And the unfortunate result I found out this year as those early students made it to capstone is they've decided not to use concrete at all because they want to be sustainable, and they're going to preference use of steel and other things in their mixes. And so I'm working with the capstone people to correct that currently, but in the future what I've discovered is that I should emphasize sustainability of concrete, but in relation to all of the other building materials. And so I'm showing a really famous plot in an Ellis Gartner paper that quantifies embodied CO2 and embodied energy for all of the different building materials and shows them in context to one another. This I also don't believe is quite fair because the functional unit is mass, and our steel members with similar capacity to concrete are going to be smaller in volume overall, but it does give a little bit more perspective on how concrete sustainability is relative to other materials. And so we were already working with a really sustainable and efficient material. That doesn't mean that we shouldn't work harder to make it even better and even lower carbon footprint. So anyway, try to show your students in reference to the global material choices, where concrete is sitting. All right, so now to the real topic of my talk is student-led experiments. These are course projects that we allow students, we give up some of our control as the professor, as the instructor, and allow students topic selection and or selection of the experimental processes that they're going to use. This is kind of similar to these old choose your own adventure novels. So we will allow the students to pick their own path and forge their own way. And so we're going to talk a little bit about the benefits, the requirements, the challenges associated with setting one of these up in your class, and I'll share some of the fun examples that have resulted from student creativity. Okay. I got to using this type of method in my class because my class was assigned to meet ABIT criteria 6, which is an ability to develop and conduct appropriate experimentation, analyze and interpret data, and use engineering judgment to draw conclusions. And all of my lab was set up with boilerplate recipes for experiments. Students came into the lab, made the mixes I told them to, did the tests I suggested, analyzed the data, and told me what the results meant. They weren't really doing an experiment, and I just couldn't justify meeting this criteria with students not actually doing experimental work. And so I started thinking about, well, how could I implement this in my class? And what I found is that the literature actually really supports use of student-led learning or student-led experiments. There's a lot of benefits associated with it. I'm showing a figure here that shows a shift in student scores within a class where they shifted from prescriptive experiments to student-led experiments, and there's a big increase in overall student learning. It also increases student engagement with the material and a willingness to work hard. When they get to choose a little bit of what they're focusing on, they'll go above and beyond normal interest in the subject because they feel a little bit in control. It also boosts student confidence. They feel like they can do a whole process rather than just a piecemeal portion. And so they feel more able to recreate that process later on in future jobs, internships, or a subsequent experimentation. Many students will also be further interested in experiential learning, and that can manifest in joining a design team or approaching you to do undergrad research in your lab. So it benefits both them and their learning and potentially us who are interested in research as well. And then if done right, this also increases student satisfaction with the course because they feel like they have learned so much, and can boost your SEI score, so your evals from students. Notice I said if you do it correctly, because there are some studies showing drops in evaluation scores because you must support the students more than you typically would in a lecture-based course. And then lastly, I view this as an opportunity to integrate creativity back into engineering. I always felt like engineering ripped a lot of the creativity out of me. You're taught the way to do it, the path, the one direction that you should go, and the set of equations to use, and not really allowed to do any of the problem solving that all of us got into engineering to do. And so student-led experiments open up the field and kind of force students to do their own problem solving and thinking, and enables them to pursue interesting topics that they want to pursue rather than what I tell them to do. All right, so how do we do this in a class? Well, in my class, I have 5 different steps. The first is the pre-experimental prep. We're not just going to release the students into the wind to do whatever they want from the moment the class starts. We need to prepare them to do that first. And so the way I do that in my class is the first half of the semester. Oh, I should have prefaced this with, my class is civil engineering materials, so we're looking at all of the different civil engineering materials: steel, aggregates, concrete, asphalt, and wood. So not just concrete, but you could also formulate a way to do this with just concrete as well. So in my class, we spend the first half of the semester, all of the materials except for concrete, with the more prescriptive types of experiments. So you can see we're starting with metals and transitioning through wood and aggregates. That allows us to approach things like stress strain curves and analysis of large data sets, play with some of the different equipment in the lab, and kind of prep them to move out on their own for the concrete. The second half of the semester moves into the student-led work, where they're leading more of that effort. So we're going to teach our theory. We're going to talk about how to do analysis. The other thing that I do in that pre-experimental prep is talk about the scientific process. So when they're doing those prescriptive labs, instead of just presenting them the process and having them go, we first talk about, what's the hypothesis for this experiment? What are we expecting to see out of it? And I have them use, with questions, compare their results to that original hypothesis. So they're actually practicing the scientific method, not just deploying some equipment and getting data. Then I ask the students to write a proposal, and this has 2 purposes. First, it allows them to formulate their plan. Second, it gets them a start on their final report. I have the students submit a literature review as part of their report that requires a minimum of 10 sources, and I have them submit 5 of those sources in this first proposal period. So they're already doing the reading and thinking and seeing what other people have done, and it also gives them some basis to formulate mixtures off of, and replacement percentages and those kinds of things. So the students are going to put their plan and their hypothesis into writing, and then the next step is they come and meet with me and have a personal conversation about what they're doing. So I have this in groups in my class. So I'm not meeting with all 100 students every semester, but instead with 20 different groups. We meet for about 15 minutes. I tell them when they come in, their role is to tell me what their plan is, what their hypothesis was, why they think that will work, and then I help them troubleshoot through issues with mixed design, or challenge them with how they're going to find and create those materials, and what kind of testing they're going to do. We're looking at things like students coming in with water to cement ratios of 0.2, or really off cement contents that would just make a complete failure of a mixed design. So trying to catch some of those early errors and prevent issues when they start their experiment. Next step is kind of the obvious one. They're going to conduct the experiment. They're going to analyze the data. It's really helpful, but not totally necessary, to incorporate some iteration in at this point. So if we can allow students to learn from what they do the first time and what they notice goes wrong the first time, and reiterate and redo their experiment, or add on to it if they find an interesting result and want to study other types of variables or extensions of variables, that even furthers the learning more than that initial experiment. And then finally, the last element that I incorporate is peer review. This also has a couple different purposes. First, it helps students to critically think about their own report. So they're looking at someone else's data and analyzing it and thinking also, oh, I could do this better like they did it, or this person is missing this whole part of the story, I don't understand what's going on, and hey, I also did that in my report. In addition, it lessens my overall grading load in the end because I get higher quality reports and higher quality writing as well. So it's helping the students, it's helping me, and hopefully it's helping them engage with the assignment a little bit more. So how do you set this up in your class? Well, I give it with a project objective that makes the purpose of the assignment clear, so that I tell them in this objective that they're both developing a research question and answering the question. I don't want them just testing 20 mixes and analyzing the data. That's not science. Science is asking a question and finding the answer. And so we need to make clear those couple elements because most of the time students have never done their own sort of experiment. So we're modeling behavior, and then I also provide them a list of beginner sorts of ideas that they can manipulate around to help give them an idea what this will look like. Right. This is kind of self-explanatory, but you also need to provide a list of materials, a list of equipment that you have in your lab, what students are allowed to bring. I also offer a very small amount of extra credit for this assignment if they create something on their own and bring it in, so if they do something creative, and that can be either a material or a test method. And so here's what we have, here's what you can use, but if you bring something else, you get a little bit of bonus credit. So some fun past ideas we've had. This has gone really well, and I realized that allowing students this freedom for all of us in the room who are probably type A personalities is really scary at first, but it actually has worked out way better than I ever imagined. Students will just take it and run. Some of the lower performing students will do things very similar to what that list was, but higher performing students will often do a complete literature review, think through the elements that are affecting the hydration of the concrete, and run with it. You can see some things here. I love the second one, use of antifreeze as a freeze-thaw damage prevention agent. These students asked if they could use my freeze-thaw chamber, and we were in the middle of some experience, and I said no. And so they decided they were going to make their concrete and then run it home and stick it in their freezer, and they took it in and out of the freezer for the next couple weeks to test and see how strength development changed and if it was damaged by freezing. We also, my favorite story was unfortunately interrupted by COVID, but I had a group of students who said they wanted to test the effect of bones on concrete hydration, and I said, how are you doing that, and where are you getting bones? And they said, oh, Professor Burris, we're going to Buffalo Wild Wings after lab today, and they're gonna take their wings, take them home, clean them off, put them in their oven, grind them up. It was gonna be awesome, and then COVID the next day. So that was unfortunate, but students are really creative and explore some interesting things that also makes your life a little bit more fun. You're not doing the same water to cement ratio experiments over and over and over again. And like I said before, extra credit is an amazing motivator. In my class, I give 5 points extra credit out of a 275-point assignment, and 99% of groups will come up with their own idea. The students are really energized by the ability to do something unique. And many of them choose sustainability related topics. You can see in the list is plastic and concrete. We've had 4 or 5 different groups pursue using waste plastics, and they'll go and find the sources themselves and cut them up or grind them or mill them or locate resources around campus to use them. So this is a way to integrate sustainability into your class and allow students some freedom and excitement. Right, so I have a couple recommendations for making this a success in your class in addition to what I've already said. There's some changes in how you implement this relative to a lecture class. First, you do need to provide some structure and guidelines. We are not just releasing students to do whatever they want because that would be, they wouldn't accomplish the goals of the course, right? So we need to provide some structure, some examples, and also some minimum boundaries. The first time I tried this, I had many students suggesting they would make 1 single concrete cylinder per mix and test that. And as we all know, we need to do a couple so we can assess variability, so we can make more than this much concrete for an entire experiment. So I now have a minimum number of samples, and we also mandated that students all run the air pot test, the pressure method test, so that they get that experience. Otherwise, they were feeling kind of left out at the end of the course. We also really want to limit the amount of new stuff that's going on during this experiment. The new is the running of the experiment, the formulating of the experimental plan, and the analysis of the data. We don't want them to be, for the first time, writing a hypothesis, for the first time learning what the elements of an abstract are, for the first time doing data analysis in Excel. We need them to practice each of those skills separately on the way to this experiment, not for the first time during the experiment. Otherwise, it will be overwhelming. We also need to provide students check-in points so that they are not procrastinating until the end of the semester. If you just assign it and let it go, nothing will happen until the week before it's due, and then all of your experiments will be really rushed and poor quality. So in my class, I set this up through the proposal check-in point. And then I work very closely with the students throughout the experimental period to challenge them to think through variables and other issues that they're seeing with their production of the concrete and testing of the concrete. And then lastly, this is a different way to engage with students. It's not a lecture style format where you can deliver the information and they hopefully imbibe it. Instead, you have to reach out to students and you have to interact with students. So for people who are outgoing, this is really easy, but it may be more of a challenge if you're more of an introvert. You can preliminarily think of some questions to ask students before interacting with them. But honestly, I just walk around the classroom and ask them what they are seeing. You know, what do you observe about this? Is this turning out how you thought it was going to? You know, what's different? What do you think has changed about your mixture? And just point out some sort of obvious things, and that can help students to begin thinking critically about what they're seeing and engaging with their experimental results as well. I do also increase my office hours around this project as well, just to make sure that students know that I'm there and ready to answer questions and brainstorm through our troubleshoot issues. So that's all I have to say about that. And here's my favorite concrete joke. I think, do I have a minute or two for questions? Okay. So if you have any questions.